this light-emitting electrochemical cells. Here are the two initial papers that introduce the concept of the LEC and the mechanism, and I invite you to look at them. Again, let's think about some electrochemistry for just a moment. We talked about this before, 2 or 3 days ago. One can do electrochemical doping of these polymers. One can do that by moving the chemical potential into the pi band, in which case you do p-type doping. And of course, we know that when you do that, there is structural relaxation and you make polarons. You can move the, or solitons or whatever is appropriate, you can move the chemical potential into the pi star band and you can make n-type doping, etc. Now in this picture, I'm using the lithium or some other, let's say lithium as the counter electrode with respect to the polymer. But we know that you don't really have to do that. We know that you can, if you want, use lithium as the counter electrode, but we also know you can use a polymer here and the same polymer here. All right, and if you do that, okay, then you can make a nice battery concept where you, with an external charging battery, you dope this polymer n-type, and you dope this polymer p-type, and of course, when you have done that, you have created a battery which will then discharge. The n-type polymer will push electrons out to the p-type polymer, and eventually it will discharge. But the thing I'm emphasizing here is that one can use the same polymer here, obviously. One can use polythiophene, one can use MEH-PPV, one can use polyfluorine on both electrodes. On both electrodes. You don't have to, but you can. Okay? So now, what do I have? In this situation, I have one polymer which is split into two parts, and in the center here I have an electrolyte, and the electrolyte, of course, is a solvent with ions in it. So the idea of the light-emitting electrochemical cell is to put all this together. So the idea of the light-emitting electrochemical cell is to make a composite which has in it the electronic semiconducting luminescent polymer, and in addition, an ion transport material with ions that can move. So instead of having two electrodes, two polymers, and an electrolyte, I'm going to make a solution which has all of that in it, and I'm going to cast a film of all of this together. So now I have a very strange material. I have a material which is an electronic semiconductor intermixed in some way with an ion transport material. Now if you think about that for a moment, you would guess, I think you would agree with me that it's likely that these two components would phase separate. This is a conjugated polymer, which is nonpolar. This is a very polar system. You can find, one can, by working hard, find a common solvent if you get things just right. But when you do solid state, when you cast the film, they will phase separate. So in your mind, you should think about wanting to have both connected paths of the semiconductor and of the ion transport medium. So I'd really like to have interpenetrating networks yet again. Okay? Interpenetrating networks are important, and I'll show you that we can do that. But let's just step back now and look at this a little from a from a less detailed point of view. So the idea is now, I put two electrodes on here, and I apply a voltage. Okay, and in here I have ions everywhere, and I have semiconductors, so I apply a voltage. Okay, and I apply that voltage, and when I get to a large enough voltage, roughly the energy gap, because what I want to do is I want to dope the polymer. So if I make this voltage big enough, larger than the energy gap, then I will take an electron from the polymer over here, and I'll put it through this circuit, and I'll put that electron over here. I hook the battery up like this, external battery. I pull an electron out and put it in over here. So it costs me the energy gap to do that. And as soon as I inject an electron here, I dope the polymer, and ions come out of the polyethylene oxide and complex in the usual way inside the polymer between the chains to dope the polymer. Of course, on the other side, I've injected holes, and I've doped it p-type. And if I push the voltage a little bit higher, then I'll have this p-type region extending in farther. I'll have the n-type region extending in farther, and what I have is a p insulator n junction. And in the middle, you're injecting holes and you're injecting electrons, and you expect to see light coming out. Okay, and you do. Okay. Now, there are a variety of ways to do this experiment. You can do it as a sandwich, but you can also do it in a surface cell configuration. So let's for example, let's for example look at this. Okay, so here's a surface cell configuration. I have two electrodes. Here's my polymer, and what I'd expect in that case is that I'd get p-type polymer here and n-type polymer here, and light coming out of the middle, right? And if I make interdigitated electrodes like this, then this whole thing here is positive and this whole electrode is negative, and so between every one of these I should get a PN and a line of emission. So this is a photograph of this interdigitated electrode structure looking under a microscope. Okay. You can't see it here, but there's a gold electrode here and another gold electrode here, and this one is positive and this one is negative, and you can see that there's been doping on either side here because the color changes, but this is done now in the dark without any backlighting of the microscope, and this is the light coming out. Okay. Here's a blown up version of that, and this turns out to be, I'll show you more data, this turns out to be a couple of microns. Okay. The polymer is, is neutral. It can be doped p-type, can be doped n-type. So if I put the battery on this way, I make it this side p-type and this side n-type. If I turn the battery around, if I reverse the voltage, then the same thing will happen, except this will be n-type and this will be p-type. These are the light out. There's light coming out here, light intensity in candelas per square meter. Here's as a function of voltage. This is the current, okay? If you go in the forward direction, you get no current until you reach a voltage which is large enough to pull an electrode out of one side and put it in the other side, to redox the polymer. And now you go in the opposite direction, and again you get no current until you get to the symmetric voltage, and then it turns on. Of course, the current is in the opposite direction because I'm reversing the bias. But you get light out in both cases, and as you can see here in this particular example, the light intensity is respectable. It's a couple of hundred, it's 100 candelas per square meter, and I'll show you that one can go much higher. If you do this with a time-dependent bias, right? So if you sweep the voltage at 20 millivolts per second or 90, or if you sweep the voltage at a very slow rate, then you get basically the curve that I showed you before, a previous transparency. But ions have to move here. Ions have to diffuse as you dope the polymer. So you would expect, and indeed you find, that if you sweep the voltage more rapidly, the ionic charge cannot diffuse fast enough, and one does not get this quasi-equilibrium behavior. You're way out of equilibrium here because you're going much too fast. So this is just, these data are proving or consistent with, but ion transport being a limiting feature. This is now supposedly the pristine polymer. I've got a nice absorption edge that is typical of the polymer. As I go to higher and higher bias voltages, it's a very thin film, okay? The optical density is not very high. But as I start to reduce the interband transition and build up some absorption down in the infrared, and so this simple data is telling us that yes, we are doping the polymer, okay? And we know from past work that the spectroscopy of N-type doping is almost the same as the spectroscopy of P-type doping. I'm looking through a PIN junction here, is the claim. This is pretty heavily doped here, N-type, and relatively highly doped over here, P-type. And I've got an indium tin oxide electrode here so I can get the light out, and I've got aluminum electrode over here. But the point I was trying to make is, since the doping levels are pretty high at this point, you get ohmic injection. Contacts are ohmic. It's very easy to get injection. Injection is natural. It's an ohmic contact because you've doped the polymer here, and gradually the dopant level goes down until this is the undoped polymer PIN in the center. So this is a battery because I've doped it P-type and N-type and P-type and N-type. If I take this external voltage out and put a resistor here, it'll discharge through the resistor. It's a battery. But it's a very bad battery, very poor battery, because there is an electronic conductivity in here also. Otherwise, I wouldn't make an LED. Okay? So if I were to take out this external battery, put a resistor here, some of the current would flow this way, and some of the current would flow internally to discharge the battery. Okay? So if you really want to make a good battery, you don't want to use a semiconducting polymer in the middle, but if you want to make light emission, you do. Okay? So this is a battery and a light emitter, so it's a light emitting electrochemical cell. But let's do that experiment. Let's charge this thing up, and then let's short it and look at the external current that's flowing. Okay? So here's what was done here. We charged up that little cell, and then we shorted it and measured the current, and sure enough, one does see current flowing through the external circuit. There's a lot of current flowing through the internal material as well, which I'm not measuring here, but this is at least proving that I made a battery because I stored the charge and it came out. Okay? And although the time scale is not very long, it is pretty long. Okay? It's whatever here, 3 minutes. It's not an RC time, not a capacitor. That's real discharging of a battery because it happens over a period of a few minutes. So we doped the polymer, we made a battery, we discharged the battery. While the battery was charged, electrons and holes are flowing inside, and you get light out. So one can get pretty good brightness. And the nice thing is with this concept is that the the injection is insensitive to the electrodes that you use. I emphasize that when you make LEDs, you really have to be careful to match the anode with the top of the pi band and the cathode with the top of the pi star band. And if you, for example, if you want to make red, green, and blue pixels, then you might have to think about using different contacts, different metals for contacts, and that's terrible. Here, the contact is self-made. That is to say, the doping itself gives you an ohmic contact, and it's all finished. So we're doping this polymer, you know, N-type here and P-type here. The scale here, as I said, is about 20 microns, something like 20 microns, and so this is 2 microns. And you say, oh my, I've got this this positive voltage here and negative voltage here. Why doesn't it short? If any place it breaks through, I have P, I have I have N. If somehow you get a spot where the P touches the N, then you have high conductivity and the device is shorted out. A capacitor stores energy, right? So the energy stored in a capacitor, 1/2 times the capacitance times the voltage squared, okay? Now, think about this PIN junction that you're looking at here, okay? There's a PIN junction here. It's a capacitor. What's the capacitance? Well, it has to do with how thick this layer is, but it's proportional to the length of the insulating of the I layer. Okay? So the energy stored in this device is proportional to the length of the insulating regime in the PIN. Okay? Isn't that nice? Okay, because now the wiggles that you see here coming from imperfections and I don't know what, you might think there's an instability, but there isn't. Because as I make these wiggles, the energy goes up. So there's like a surface tension here, which tries to make this, make this thing straight. Okay, and it doesn't quite succeed, but you also don't get huge fingering and breakthroughs and shorts. So simple thing here of the energy stored in this capacitor gets bigger if you have more wiggles. So it's like a surface tension. It's like this is a string that's being pulled. I want to make an interpenetrating network. I would like to make the distance between, I'd like to have phase separation of the polymer and the conjugated polymer and the PEO lithium, but I'd like it to be on a micro scale with very short distances, because in order for this device to work, the ions have to move from the polyethylene oxide component into the semiconducting polymer as it's doped. So there it is. Okay, that's a photograph. That's an electron microscope picture of the interpenetrating blend. There's a bar here at 500 nanometers, 5,000 angstroms. I don't remember which is which. This may be the conjugated polymer, or it might be the polyethylene oxide. I don't remember. But you clearly can see the interpenetrating network. And the way he did that was to use this bifunctional molecule. On one side, it likes PEO, and on the other side, it likes MEHPPV. So this bifunctional molecule helps the system form into this interpenetrating network because this bifunctional molecule likes to be at the interface. It's like a surfactant making oil in water. And notice what happens, okay? So here's the light intensity, and we're pulsing on the device. And if you do not put this molecule in so that you have a much bigger length scale in the structure, it takes a long time for it to turn on. This is 1 second here, the log scale, okay? But when you put the OCA in and you make this microstructure, improve the microstructure, then instead of 1 second, it's whatever, 10 milliseconds. So it works, okay? Now, I'm not claiming it's optimized, but you see the idea. And there are a number of important things here. I mean, the ability to manipulate the microstructure by using a surfactant-like molecule, a bifunctional molecule, is very important. Okay? In this particular case, we want to have the semiconducting polymer and the ionic transport polymer deeply intermixed, and so I need to find a molecule which will do that. Okay? In the case where I want to make a conducting blend of a metallic polymer and whatever PMMA, then I need to use a bifunctional molecule which one side likes the conducting polymer and the other side likes the PMMA. And how did I do that? Remember how we did that. We did that in the case of polyaniline, slightly different way, by using a counterion, which was the DBSA. And the dodecylbenzene sulfonic acid, remember, is SO3 minus with a phenyl ring and with C12H23 chain on the end. This stuff likes PMMA. This thing likes the charge of the polyaniline, and you can make networks. In this case, I've got two different polymers, but if I'm clever about what I choose as an additive in this case, this is just an additive. In this one, this is serving as a counterion. In this case, it's just an additive, but you can use it to control the microstructure. We saw a little bit of information about the width of the emitting layer from the photographs that I showed you a few moments ago. Now, I want to do a different experiment. This is I've turned on the voltage, so I have a PIN junction. Okay? PN junction has a built-in potential. So now what I want to do is something which is called beam-induced currents, OBIC, optical beam-induced currents. Okay? OBIC. It's nothing more than photovoltaic effect. Okay? So here's the experiment. I get a laser, and I just translate the laser across here. Okay? And here, of course, the laser is on the electrode. I get I'm making no electron hole pairs. All right. Here, the laser is in the N-type region, but in the N-type region, there's no electric field. All the electric field is across the I region in the PIN junction. Okay? When I get to the I region, I'm making electron hole pairs in the presence of a built-in potential and electric field. I got a solar cell. They separate. I get current. When I go over into the P region, again, there's no electric field. So I can directly measure by the photocurrent the width of the PIN junction using this optical beam-induced current methodology. And here are the pictures. Okay, so here's the two electrodes. As I said, they're a little more than 20 microns apart, 22 microns. And I start on one side, bringing my laser beam along. And the laser beam is focused down to, less than a micron, so that I have good resolution. And I don't see any current. And then when I get to this point, current starts to go up, 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 and I'm going through the I region of the PIN junction, and then I come back, okay? And that was done for at 5 volts applied. Here's 4 volts applied. Here's 3 volts applied. Now, what am I measuring? Okay, I got the fixed light intensity, scanning this thing across. I'm measuring a built-in electric field. Okay, there's no electric field here. There's no electric field here. There is electric field here, and I'm measuring that electric field. So I can integrate the electric field. Here's the electric field as a function of distance. If I integrate that electric field, I get this curve, these 3 curves. Beautiful. There's the PIN junction. Okay? Here's which is which. This is P, this is I, this is N. The PIN junction, the width of it is right here. Okay, you can see it. The width of it is, 2 microns. Lovely experiment. Photovoltaic experiment. So while we're doing that same experiment, we can also look at the photoluminescence of the material, right? My laser's coming along here, and I'm detecting this current, right, that I just showed you. But this is, this is MEH PPV here. So it should be luminescent. So as I scan the laser across, I should see luminescence in it. But if you dope it, you should quench the luminescence. Right? This is the current, short circuit current of that little photocell. And now I'm going to show you the luminescence that you see when you scan across. So before I apply any voltage, of course the luminescence turns on as soon as I get the laser in the material where, here's one electrode, here's the other electrode. So I get good photoluminescence all the way across, okay? Basically uniform. As you start to dope the material, and this is the highest level of doping. I don't remember which is positive, which is negative. You're doping one side P-type, the other side N-type. And there is, here a little peak in the photoluminescence, which there had to be because you saw it on the photograph. But obviously, it would have been better if this were all the way up to here. So the PIN junction, the I region, is partially quenched. Maybe that's because these conducting P and N regions are so close by. I don't know. This is not a good thing, okay? Because it tells us that the photoluminescence here is already down by a factor of 5 from the pure material. And remember our discussions of yesterday or the day before, the photoluminescence is the maximum quantum efficiency is the maximum you could ever expect for the electroluminescence. Okay. So this is a lovely device, many, many advantages. Okay. This I don't like. Maybe it can be fixed, but you see the point. I want to measure the thickness of the barrier, of the insulating region, the PIN, in the sandwich configuration. Okay? And the claim that I make is that at 0 voltage, you've got a metal electrode here and a metal electrode here and a dielectric in between. We know that the capacitance is epsilon A over D. So there is some epsilon here, and whatever that epsilon is, the capacitance is proportional to the area, of this device, and it's proportional to 1 over the thickness. And then the idea is that when I go above the injection threshold, and that injection threshold should be when the applied voltage is equal to the energy gap over the electric charge, then I claim I'm doping this p-type and this n-type. This is now part of the electrode. This is now part of this electrode. The insulating layer is here, and the thickness d prime is much less than the thickness d, so the capacitance should go up. And here are the data. It's in terms of complex impedance. This is the imaginary part of the impedance. But here are the answers. Okay, in the pristine state, at voltages below the threshold, the capacitance for this little device, whatever size it is, was about 2.1 nanofarads, epsilon A over D. Okay, when you go up to 3 volts, it turns out to be 2.6. Okay, the area hasn't changed. But now, so this gives us a hint that the thickness of the device has changed as suggested by this photograph, and that d prime is about 0.8 of the total thickness. This is a collaboration between our group and the Los Alamos group, where they were doing electroabsorption. Electroabsorption gives you a way to measure the internal field inside a device. So what is electroabsorption? In a very schematic sense, right? So here's the absorption coefficient in zero field. Now, when you apply a voltage, you get a slight shift in the absorption edge. So when you put on a voltage, this absorption curve shifts slightly, okay, like this. And if you put on, and if you take it away, it goes here, okay? So if you measure that shift as a function of the voltage, then you have now learned the calibration. Delta H bar omega, it's the shift in the absorption edge as a function of the external field, looks like this, okay? Now I'm going to take these data and I'm going to do electroabsorption on the light-emitting electrochemical cell and measure the internal field, okay? I don't know what the internal field is, but all I have to do is look to see how big this is, look at my calibration curve, and I can see. Now, here's what you expect. Okay, you have to think about this. It's quite interesting. At a voltage, I apply a voltage, but it's below the threshold for doping. That is, the applied voltage is less than the energy gap. Got a capacitor. It's just a capacitor. So, of course, on the electrodes of my capacitor, I get a negative charge here and I get a positive charge over here. But there's a dielectric in between, okay? And that dielectric in between is polarizable. And so ions move until they compensate this charge. Ions are movable inside this material. It's an ion transport material. So now this is a little capacitor, parallel plate capacitor, where the positive charges are on the aluminum and the negative charges are ions just inside. I've got ionic, it's like any ionic solution, okay? If you put a voltage across an ionic solution, the electric field in the solution is zero. So all the electric field is in the double layer at the interface. This is the same. The electric field inside should be zero. And of course, if the electric field inside is zero, there's no shift in the absorption edge here, and that tells me that, so I can check it. Okay. Now when you go above threshold, and you start to dope the polymer, it's very different. Okay? Now you inject electrons and you inject holes, and those electrons and holes are compensated by ions, and you get doping, but this is neutral and this is neutral. This is just now part of the electrode because it's a conductor. And this is part of the other electrode because it's a conductor. So now I have, again, a capacitor in which all the voltage drop is across here. The electric field is not zero, and you should see a shift in this. Okay? And you do. It all works out. Okay? So the mechanism is becoming more and more clear. And then because I have calibrated this phenomena, I can take from the electroabsorption signal the strength of the field. Okay? Field is 0, goes up to whatever, 10 to the 6 volts per centimeter at this point. Let's take silicon. Let's make a PIN junction. How would we do it? Well, let's say, for example, the old-fashioned way would be to take a crystal and just pull it out of the melt, and let the melt be slightly p-type. And then at a certain time, I compensate that to make it neutral. And then a little bit later, at least you can imagine conceptually, I make it n-type. So I make a PIN junction. We know how to make these things. And of course, that's all done. You can do it by diffusion, or you could do it in the melt or whatever, but it's all done at whatever, 800 degrees centigrade or something, where the diffusion of these ions, phosphorus and silicon, phosphorus dopes silicon n-type. But in order to put the phosphorus in, you either have to put it in the melt or you have to diffuse the phosphorus in at a very high temperature. Because at room temperature, these ions don't move. So if you take a PIN junction of silicon, it'll be there forever because the diffusion constants are so slow. Okay? Now it's a very nice thing, very nice science, and a very nice feature that I can take this light-emitting electrochemical cell and I can start with a neutral material, put on a voltage, and create a PIN junction. Turn the voltage off, the PIN junction goes away. Put the voltage on an opposite way, the PIN junction is reversed. It's very nice. Okay? It also would be nice to have a frozen junction like you have in silicon. Okay? So how could you do that? So that's the idea. So what we'd like to do is to create the junction, freeze it, so that it's permanent. Okay? Now the simplest way to do that is to take the materials that we're playing with so far, where the diffusion constants are very high at room temperature, just cool it down to 77 degrees. Nothing will move. Okay? That's not a practical device, but it proves the concept. So that was the first thing that was done by Jun Gao, and you can prove everything. So here's the idea: you create the junction at room temperature by using the redox doping, as I've shown. You keep the voltage on, and you lower the temperature while the voltage is on, and then the junction is frozen in. And then you can treat it just like a silicon PIN junction. It should have a built-in potential. It should be a solar cell. It should be a diode, and all those things are true. Now, I pre-biased it at 4 volts and I cooled it down to 77 degrees. And now the IV curve is not, symmetric. Now it's a diode, one way only. Now I get light out, and I can just go up and down on this curve because the ions don't move any longer. If you look at the current versus bias at room temperature, where the junction is forming and reforming, the ions have to move, and so you tend to get hysteretic effects of this kind, okay? because you're building up the ionic doping here. You're building up you're creating the doped regions here. You're undoping over here, and there's a natural hysteresis both in the current density and in the light intensity. But if you freeze the junction and go down to low temperatures, then it's just it's just a PIN junction like you would find in an inorganic semiconductor. At room temperature, where the ions can move, I haven't emphasized this, but at room temperature where the ions can move and you've got an active electrochemical cell, you have all the difficulties of side reactions of electrochemistry. The devices don't last very long. They decay very rapidly. But if you have frozen junction, then you can push the voltage up much higher, push the current up much higher. At room temperature, see, I mean, it just won't go and it's starting to fail. This, by the way, is not reversible. But if you freeze the junction and cool it down to 100 degrees Kelvin, you can drive much higher currents, and you can do that in a reversible way. So the thing works. And this is the classic proof that you've got this built-in junction. And this is just showing you that there's that basically that diode functions as a solar cell. So here we pre-biased it in one direction, and this is in the dark, and this is in the light, and the current flows in the appropriate direction. Here I pre-bias it in the opposite direction, and so the polarity of the solar cell is dependent on the pre-bias and whether the PIN, it's a PIN or a NIP. You get this one or this one. The question is, can we find a way to make a frozen junction at room temperature? Well, the idea would be to find there are two ways to do that. One way is shown here. We want to find a system where the ions are where there are no free ions at room temperature. But if you raise such a system to high temperatures, you get free ions, you can build a junction, and then you can come down to room temperature. This sort of works, okay? Lithium salt forms a complex with crown ethers, is very well known, and at room temperature, all those ions are trapped in crown ethers. They're not free to move. But the binding energy of the lithium ion to the crown ether is pretty small. So if you raise the temperature up to roughly 80 degrees C, the lithium ions become free to move. You can build in the junction, you can cool it down to room temperature, and you can use it. Now there's another approach which is in my mind somewhat better, and I'll remind you that there's a large group of scientists who are working on nonlinear optical materials, okay? Second order NLO. And the way they do that, for example, is they take a chromophore which has got a dipole moment, and they put it into a host polymer, and they then put a large electric field on, and they orient the dipoles. Okay? Here's orient the field. They call it poling. And of course, in that case, if you do that and you turn off the electric field, they just become randomized again, and your nonlinear material doesn't work. So the first generation to improve that was to use a host polymer with a high glass transition temperature. You raise the polymer temperature up above the glass transition temperature, then you can orient and pole the guest. And then when you go below the glass transition temperature, you turn off the field, and these are frozen in. Works pretty well. But slowly, they decay. So the next step that people have done is to do what I said, have a polymer which is at a high glass transition temperature, do the poling at high temperatures, but now have an additive in there or have a polymer in there which is cross-linkable. So you pull it, and then you cross-link it. Maybe by UV, I don't know, somehow you cross-link it. And now these ions cannot relax, and so now you've you've frozen in the orientation of these dipoles. Okay? That whole methodology, you know, has been heavily explored. We haven't done this yet, okay, and I don't know if I will, but you could certainly imagine the same sort of thing. Okay? Use a high glass transition polymer. Ions will move at high temperatures. Cross-link it, bring it down to room temperature. It should be very effective. I mean, if you can prevent a molecule from rotating, a small single molecule from rotating, then I'm absolutely confident you can prevent ions from moving over macroscopic distances. So one should be able to pursue this point and get frozen junction. It's basically going back to silicon PIN junction with organics. This is, again, I'm using this surfactant bifunctional molecule. You can get 20,000 candelas per square meter at, here at 6 volts. That's pretty damned impressive. And the 5.6 lumens per watt quantum efficiencies, which are high. So the point here is to leave you with the correct impression that one can get high performance devices out of this. And in the frozen junction regime, you can get fast time constants because because ions do not move. So the time response of the turn on of the light is just, like in an LED where it's only electronics. So this is an RC time constant decay. It has nothing to do with the ions. One is getting 20,000 candelas per square meter at 5 volts in spite of the fact that there's some heavy quenching here. So it says if we really went seriously to work on this device configuration with the goal of getting the junction to be more well-defined or whatever so that we did not lose this whole factor, we might do much better. Okay? And the basic point is that you're not injection limited here. You have really good fast cell injection because you've doped the polymer. So the frozen junction LEC concept works, but it is an unfinished story. I mean, we haven't really pursued it. The room temperature operating LEC is very interesting. We learned a lot, but the lifetime of the device is just not even close to what we can get in LEDs, and that's why the what I'll call conventional polymer LED is what is being commercialized. It is possible, in fact, I expect that if we really pursued the frozen junction approach, we could get long lifetime in the LECs, because the important thing is that once you have turned off the electrochemistry, then the side reactions are less probable and probably get a longer lifetime.